Well, let's continue our work in our Chapter 19 Lipids chapter, focusing on Section 4, Triacylglycerols, which are known as fats and oils. We're going to sound that word out together. Hear the word tri, meaning three. Acyl is a functional group we'll learn as the O linkage, and connected to a glycerol molecule, triacylglycerols. Commonly, we hear these called triglycerides, and that might be the more common or familiar name. We can see that they contain three esters formed from a glycerol backbone and three molecules of a fatty acid. And I call the glycerol molecule the backbone. When we look at our general structure here, the glycerol molecule is a 3-carbon chain, and each one of those carbons has the hydroxyl group connected to it. So as we see, and just kind of complete each octet, we'd have 4 bonds to each of those carbons, but the key function here of the glycerol is those 3 hydroxyl groups. And they're going to connect to fatty acids, which we looked at in our second section. Really is just a very long carbon chain with the COOH group. Trying to write and talk, and I fell flat on my face. So this is the COOH functional group. So this is what we call a generalized block diagram of a triacylglycerol. The backbone, going kind of perpendicular to the page, is the glycerol molecule, and the fatty acid chains, those long carbon chains that contain the carbonyl carbon. Well, let's get a little more specific with our examples. I mentioned that here is the molecule of glycerol. Glycerol is a 3-carbon chain, and each of the functional groups on those carbons is the hydroxyl OH. In addition to the glycerol molecule, we have 3 fatty acids. And notice that the fatty acids may be the same or they may be different just based on the length of the carbon chain. So we see that designated as R, R prime, or R prime prime. They may be the same or different fatty acids, and fatty acids are categorized as the number of carbons that those groups contain. And when we combine those two together, we get a triacylglycerol. And notice that these again are ester linkages in this molecule, and those are highlighted in red. We see the glycerol backbone and the 3 unique carboxylic acid groups, and when they attach through an ester linkage, we get something known as a triacylglycerol. These triacylglycerols are categorized really based on the carbon chains of the fatty acids, and we'll see them as coming out as solid fats or liquid oils. We can talk about simple triacylglycerides that are easy to identify based on the fact that the 3 carbon chains coming from the carboxylic acid group, the fatty acid groups, were identical. Oops, that's the highlighter, Linda. So here I go, identical fatty acids. So in your general structure, this would be R, R, R. There is nothing unique about them. And we also want to kind of just emphasize the importance of this word here, saturated. When you see saturated, it means that there are all single bonds. There are no double bonds in this structure at all. So a simple triacylglycerol repeats the same fatty acid chain for all 3 attachments to the glycerol backbone. Here is our 3-carbon chain, the glycerol backbone, and here are 3 identical fatty acid chains, giving a simple triacylglycerol. If you hear the term mixed triacylglycerol, it just means that there are different fatty acids attached. All 3 could be different, 2 of the 3 could be different, however, they're just not the same. So here we would have a triacylglyceride where two of the three components from the fatty acid are the same, and here this one would be different. Also notice a term now that when I see a double bond in the structure, the vocabulary for this now is unsaturated carbon chain. So I see that it contains a double bond, making it an unsaturated carbon chain. We learned that double bonds ended in an ENE. All single bonds came from the alkane family and ended with an ANE. Also make note of the configuration that this is a cis conformer, the conformation of the double bond. Remember what cis means? You locate the double bond and both groups are coming out the same side, so that represents the cis conformation. Just to compare that, if we see a double bond and they're coming out the opposite sides, we call that trans. But when we're looking at natural oils and fats, we're looking at the cis configuration always. Trans occurs in more synthetic molecules that are made. Cis occurs in nature. So the saturated triacylglycerols, saturated all single bonds, saturated. They contain all saturated fatty acids and come to us from animal fat. Animal fats are always solids at room temperature. So here is a triglycerol atom, triacylglycerol atom, and it's saturated because nowhere in those carbon chains do I find a double bond. All single bonds mean that it is a saturated triacylglycerol, and the origin for saturated fats are animal fats, lard, things like that. And you'll see that they're solids at room temperature. Unsaturated triacylglycerols contain at least one double bond and therefore are referred to as unsaturated. So unsaturated means at least one double bond, and it will always be in the cis conformation. These will always be liquids at room temperature. Just think of your common vegetable oils as a source of an unsaturated triacylglycerol. Monounsaturated fats contain just one carbon-to-carbon double bond. Polyunsaturated triacylglycerides contain many carbon double bonds. And this is a very important statement. It's going to help you recognize physical trends, physical properties related to boiling point. As you increase the number of double bonds, you decrease the melting point. The more and more double bonds, the lower the melting point. Remember we had said fats, which are saturated, have no double bonds, so therefore they're very high melting points. And these oils, which are unsaturated, have lower melting points. The more double bonds, the lower the melting point. Fats are solids at room temperature. Liquids are oils are liquid at room temperature due to their increasing number of double bonds. Triacylglycerols, general feature. Notice we're just kind of emphasizing the general structure. So here we're looking at the three fatty acids, and I notice that this particular fatty acid contains no double bonds. This picture of the fatty acid contains no double bonds. But in the third group, I finally can see a double bond in the structure, and it is the cis configuration. That doubled bond, just the one presence, all it takes is one to be labeled an unsaturated triacylglycerol. Emphasizing physical properties. Fats have higher melting points. They are solids at room temperature. Fats are derived from fatty acids with few to no double bonds. Oils have lower melting points. They are liquids at room temperature, and they are derived from fatty acids having a larger number of double bonds. The more double bonds the structure has, the lower the melting point. Animal products give us saturated fats. Animal products give us a saturated triacylglycerol. From animals, they contain no double bonds. From vegetable products, such as olive oil, canola oil, lots of varieties, we can see that they are unsaturated triacylglycerols. And it's unsaturated when I recognize a double bond in the cis configuration. Time to practice. Let's draw the structure of a triacylglycerol formed from glycerol and 1 molecule of stearic acid and 2 molecules of oleic acid, and bond the stearic acid to the secondary alcohol group on the glycerol backbone. So at this point, I gave you that handy chart to look up, that table 9.2, and it was the front cover of your note pack, and I just wanted it for easy reference so you didn't always have to flip back to your book and so forth. Take a moment and find that chart, front of your note pack, and find those formulas for stearic acid and oleic acid. We need those to be able to do this group. Come back when you find them. Okay, so you're back. Let's talk through our strategy. The first step I want you to do on your paper is start by drawing the glycerol backbone and draw it perpendicular up and down on your page. It is a 3-carbon structure, and the OH hydroxyl group comes off of each of those 3 carbons. This is the structure of glycerol. We're told then what we want to do is to add the stearic acid to the secondary carbon, and we want the oleic acid ending up in position 1 and 3. So kind of putting the pieces together. And I know you found, I asked you to find the stearic acid formula. And down here with an unsaturated fat, we found the oleic acid formula. We needed that to know what to attach to our process. So let's put it together. We had in the very beginning here, 1 plus 7 is 8. 8 carbons prior to the double bond. Between carbon 9 and 10 is the double bond. And then 7 more carbons to the coup. 1, 2, 3, 4, 5, 6, 7 carbons, just a straight chain carbon, is the beginning of the oleic acid structural formula. Notice that between carbon 8 and 9 is a double, I numbered wrong here, 8 and 9, 8 comes after 7. In carbon 8 and 9, there's a double bond, and it must be the cis conformation. Then what do we see? Well, there's 7 more carbons, just a straight chain, and then the coup ending it all. I think what I'd like to do, and if it's all right with you, I'm going to renumber. We're going to end up at the same place, and I know you hate to erase, but the reason I want to emphasize renumbering is that I realized this carbon gets priority, and it needs to be called carbon number 1. And when we're just counting how many carbons are in place, our structural formula won't change, but I'd like to emphasize that that's carbon number 1. And now when I count 2, 3, 4, 5, 6, 7, 8, double bond between 9 and 10 in the cis conformation. And then we go 11, 12, 13, 14, 15, 16, 17, 18 carbons all together. Here's carbon 1 plus 7 more. We're at carbon 8 so far. Between carbon 9 and 10 is the double bond. And we have a total of 8 more carbons after the double bond. And we think about the total number of carbons, we ended up with 18 coming from oleic acid. And in position 1 and 3, you're just going to repeat those two structures. So locating the double bond between carbon 9 and 10 in the cis conformation, meaning that both of those carbon branches come down the same side of the double bond, and we repeat that twice in the first and the third position on the glycerol. Here we have an 18 carbon straight chain. Carbon number 1 is attached to the carbonyl carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons were drawn in that long fatty acid chain. Glycerol is the backbone of this structure. We have now identified both of the fatty acids that are going to attach to the glycerol and create our triacylglycerol product. This slide is just repeating our glycerol backbone, the 3 fatty acids we just drew, and now we're going to put it all together to create the triacylglycerol. And here we see our ester linkages. The ester linkages in our compound coming from a C double bond O. Here is the glycerol backbone, carbon 1, 2, 3. So in this structure, carbon 1, 2, 3 is the glycerol backbone. And we attach that to each fatty acid, creating the ester linkage. We call this a dehydration because we're removing a water molecule for each site of attachment. Let's practice another. Repetition's our friend while we're learning. Draw the structure of the triacylglycerol that contains 3 molecules of stearic acid. Okay, so let's simplify this. Glycerol is a 3-carbon chain. So I'm going to put 3 carbons. And I understand glycerol had the site of the OH group. Just to remind ourselves, glycerol is a C, 3 bonds, 3 carbons, and coming off of each of those carbons is an OH. Remember that as we link these together, we form an ester conformation. The ester conformation is going to take the H and the OH to make a water, connecting the oxygen to the carbonyl group of the acid. The oxygen from the glycerol remains. So this first step is the glycerol backbone. What it now connects to is the C double bond O from the fatty acid. This part, C double bond O. And what's left? Well, the repetition here is CH2 taken 16 times, and finally the chain terminates with a methyl. And since this is all the same fatty acid, we repeat that chain 3 times. Let's make it just one more time to emphasize. The original molecule of glycerol sitting next to the original carboxylic acid, whatever that acid might be. We take off the H from the glycerol. We take off the OH from the carboxylic acid. And those come together, HOH is going to create 3 water molecules. We're dehydrating. So the site of the new attached bond, the new bond that forms, is now from the oxygen to the carbonyl. That's the new CO bond. Let's try another. Here's the glycerol. I've removed the hydrogen, the oxygen remains. The site of attachment is to the carbonyl, carbon of the fatty acid. And the oleic acid, remember right here, that's the carbonyl carbon. That's what's corresponding to what I just drew. What's left is a series of CH2 taken 7 times, attached to a double bond, attached to a group of CH2 taken 7 more times, and the chain terminates with the methyl group. Repeat that 3 times and you'll have this structure. This is an unsaturated triacylglycerol. I see the cis conformation of the double bond. There we got it. These triacylglycerides are very important in terms of a biological molecule. These fats are used to build cell membranes, coming up in our next section soon. They insulate the body, storing fat and energy. It's recommended that we take no more than 20 to 35% of a person's caloric intake should come from the lipid family on our food pyramid. And that these high intakes of saturated triacylglycerides is linked to heart disease, and that's assimilated with cholesterol and the cholesterol plaques that build up inside arteries, resulting in high blood pressure, possibly heart attack, and even stroke. It allows us to emphasize the importance of a balanced diet to prevent high cholesterol results in cardiovascular disease. And we can look at those one more time as sources of good fats and bad fats, if you will. So foods that are rich in saturated triacylglycerols come from animal derivatives like fatty red meats, cheese, butter, fried foods that are in saturated fats. And of course, ice cream is an animal product as well. No double bonds in the carbon chain, solid at room temperature, increases blood cholesterol level. On the opposite side, we have foods that are rich in unsaturated triacylglycerols deriving from plants. Plant oils, nuts, soybeans, fish, and so forth give us these unsaturated fats, those that have cis double bonds, giving a liquid conformation, and they actually work to decrease blood cholesterol or increase your health, your cardiovascular health. Foods that are rich in trans triacylglycerols are margarine, processed foods, fried foods, and some baked foods. Let's emphasize this word trans. These are not natural. We do not find the trans configuration in nature. The trans configuration of a double bond is something that is found only in processed foods, making them even more unhealthy than the saturated fats that have cis configurations. This is why some people will argue that eating butter is actually healthier for you than eating margarine. Margarine is high in trans triacylglycerol, whereas fat is derived from an animal product, which is the cis conformation of the saturated triacylglycerol. And emphasizing that would show unsaturated lowers the risk of heart disease. It does so by decreasing the level of our cholesterol. They're formed from omega-3 fatty acids, which have proved to be very beneficial in lowering the risk of heart attack. Stay away from triacylglycerols with the trans configuration. Trans fat is usually synthesized instead of occurring in nature, and actually works to increase blood cholesterol levels. With the chemistry of triacylglycerols, it's very similar to the ester formations. Adding water breaks that ester linkage and you're back to the original components that the triacylglycerol was built from. And we'll see that the presence of an acid, a base, or even a biological enzyme works to break the ester linkage. The ester linkage we see here drawn in red. The red ester linkage in the presence of water simply hydrates back the molecules. We get back the original glycerol, we get back the original fatty acid, the OH adds to the acid, the H adds to the glycerol molecule. So when we dehydrate, we read the reaction from this particular section where we dehydrate, we remove water to build the triacylglyceride. Through the process of hydration, hydrolysis, we add the water back in and the bonds then break. So when I look at this particular structure, we're just asked to draw the products when this triacylglycerol is hydrolyzed with water. And it's done so in the presence of sulfuric acid. So adding water across the double bond, so you'll see plus water, in the presence of an acid catalyst. Could be H+, H2SO4, doesn't matter, just so that you see it's in the acid catalyst. Well, what we want to find here is the backbone called glycerol right here. The 3-carbon chain of glycerol, 1, 2, 3. The ester bond is going to break between the O and the carbonyl, and that will form the fatty acids that are linked to the glycerol molecule. So always their glycerol backbone will come out. Glycerol is a 3-carbon chain. Each of those carbons has the OH group attached to it. Just to complete the octet, we know they're there, so I'll just add on those hydrogens. And, well, let's count. Let's see what we have. I know that the first fatty acid, I'll highlight in green here, was going to originate at carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons there. So that means our first will have a C double bond O, OH. That's carbon number 1. Right, as we've added it back, the HOH adds back, and so we're back to the original carboxylic acid. And we just have to add, I'm going to do it this way, CH2 taken, is that 16 times, plus the the end carbon would be a CH3 group. So carbon 1 plus 16 gives me 17, and here's carbon 18. So that would be one way to write that first product. What are the odds this would be the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Nope, they're different. So the first contains 18. The second would contain a total of 16. So the carbon number 1 is the carbonyl. We're going to have CH2 taken 14 times, terminating with the methyl group, giving me a total of 16 carbons. And the third, here's the first carbon. I'm running out of room, so I'm going to need to write the third one up here. So I'm just going to model. That's the third carbon. We have the carbonyl, CO, and it's now been restored to the carboxylic acid, OH. We have 1, 2, 3, 4, 5, 6, 7 carbons that are CH2s. I notice between carbon 8 and 9 is a double bond, so I'm going to show you that double bond between carbon 8 and 9. I numbered wrong. I'm so sorry. I just caught that because it doesn't ever happen at that particular even number. Carbon 1 is the carbonyl. 1, 2, 3, 4, 5, 6, 7, 8. I knew it had to be an odd number. Between carbon 9 and 10. So that first carbonyl, carbon 1, and then we had 1, 2, 3, 4, 5, 6, 7 carbons of CH2 group. Between carbon 9 and 10 was the double bond. And then we're back to CH2s. We're back to CH2s, and how many of them do we have in a row? 1, 2, 3, 4, 5, 6, 7, 8. There's 7, and then the last one will be, of course, the methyl group to terminate the chain. So there are 11, 12, 13, 14, 15, 16, 17, 18 carbons in that total chain. Let me count my math. 1 plus 7 is 8, 9, 10, 17, 18. I did it. 18 carbons. And between carbon 9 and 10, we placed the double bond. To emphasize, all we really did there was to just separate out and draw for us what was coming out. And that's exactly what I tried to draw, but I did so in kind of a shorthand method. We had stearic acid, palmitic acid, and with this chart, I'm just emphasizing, you do not need to memorize these particular structures. You have that access to that table I gave you in the front of your notepad. Try drawing the formula for the hydrolysis of each triacylglycerol. You may certainly shorthand your answers. So what I mean by that is, let's find the glycerol backbone. There's the 3 carbon, and we simply break the ester linkage. We break the ester linkage, restoring the glycerol. And the glycerol is restored by protonating the alcohol back. We can finish the octet with those hydrogens. So that's a given. In both A and B, you will produce the glycerol molecule from the backbone. And when you break the ester linkage, this is carbon 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons will be drawn. There's carbon 1. We have a CH2 group. How many of those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those, and it terminates with a carbon methyl CH3. That is 14 carbons altogether. How about in that second position? Is it the same? Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's identical, so I'm going to have 2 moles worth of that. Let's check the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's also identical. So I have 3 identical molecules of a 14 carbon carboxylic acid. That came out nice. And in letter B, again, always we restore the glycerol molecule back to the protonated form of OH. We know that to complete the octet on the carbons, we add those hydrogens. So that's our glycerol backbone. I suspect this particular carbon is unique. I don't see a double bond, so let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's 14 carbons. So that's exactly what we drew up there. CH2 taken 12 times. I didn't make that very neat. Let me rewrite that. CH2 taken 12 times, and then of course the terminating CH3. Here, 1, 2, 3, 4, 5, 6, 7, 8. Then carbon 9 and 10 have a double bond. 11, 12, 13, 14, 15, 16. Is this the same? 1, 2, 3, 4, 5, 6, 7, 8. Double bond, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Nope, it's not the same. So that just means we have to add on to finish the product side. So the second group would again have the OH restored. It leads to a CH2 series taken 1, 2, 3, 4, 5, 6, 7 times. Then I see a double bond between carbon 9 and 10. And then another series of CH2s, 1, 2, 3, 4, 5, and it terminates with the methyl group. And the very last chain, again restoring the hydroxyl component to the carboxylic acid, that's carbon 1. And I have 1, 2, 3, 4, 5, 6, 7 CH2s, followed by the double bond. So I'll write that as CH, double bond CH. And then I ran out of room here, so I'm just going to have to continue. We have another group of CH2s. 1, 2, 3, 4, 5, 6, 7 of those, followed by the methyl group at the end. So this particular chemistry, the hydrolysis, breaking them back apart, has many implications for human biological functions. We know that triacylglycerols is commonly stored in adipose cells, fat cells, below the skin surface and in breast areas, surrounding the internal organs, anything that needs insulation. Kind of an interesting note, the number of adipose cells is constant. So really, when you're gaining weight or losing weight, you're not changing the number of fat cells. You're just causing them to swell or shrink based on the amount of adipose tissue inside the cell. To metabolize these triacylglycerols for energy, we use an enzyme called lipase. If it's plural, lipases. Anytime we see, as we progress in the biochemistry portion of our semester, that ending of ASE, we'll learn that that's how enzymes are named. Enzymes are nature's catalysts. They speed up these chemical processes. The complete metabolism of a triacylglycerol yields carbon dioxide, water, and a great deal of energy. We've learned this type of pattern really is called a combustion reaction. The combustion reaction releases energy as we metabolize these great long hydrocarbon chains. And that's the process really of digestion and the entire focus of the metabolic pathway is to release energy. It's about 9 kilocalories for every gram. Knowing proteins and carbohydrates releases about 4 kcals per gram. So when you're burning fat, you're releasing a heck of a lot more energy, almost twice as much energy as you are when you're burning proteins or carbohydrates. In our next section is very similar to what we've just been talking about. So I'm going to add this on here as well, the hydrolysis of triacylglycerols in soap synthesis. The only difference here now is that a soap molecule is a metal salt, a metallic salt of the fatty acid. So let me just emphasize, if it's a fatty acid, we have the proton added on. Cu is the acid. And if it's a soap, through saponification, we can create this metal salt. Instead of having OH at the end, we could have the carboxylate anion, which is a negative ion. And of course, we know that wherever there is a negative, we have to have a positive, and this then creates a salt. So this negative ion, carboxylate ion, with its first name sodium or potassium, whatever it might be, creates this compound that through saponification to create soap molecules. So we have a very polar head here with the charged ion of sodium and the charged polyatomic negative region of the carboxylate anion, and then this long hydrophobic chain. So this is what's so cool about soaps, is that it can work to dissolve greases, other nonpolar solvents with its hydrophobic chain, and it could still work to dissolve ionic compounds or polar compounds based on the polarity of the salt, the hydrophilic tail. And this is like an example of a salt through saponification. So here we have our triglycerol here, the 3-carbon chain. as triacylglycerol contains a cis configuration. So it is an unsaturated triacylglycerol, and it's showing me that because it's coming from an oil. In the presence of a strong base, such as sodium hydroxide, this process is called saponification. And all that means is when we break the ester linkage, just as we did a slide before through the process of hydrolysis, we break the ester linkage, but instead of ending at the acid, we end with a salt. Sodium oleate would be the name of this particular salt, and it's just really the major ingredient of any bar soap. Saponification, in the presence of a strong base, creates the salt known as soaps. And we can try one here. What is the composition of the soap formed by the basic hydrolysis of each of these triacylglycerols? So the composition of the soap, we're going to break the ester linkage, and instead of forming the Cu, we end it with a sodium ion to form from the saponification. So of course we know that the triglycerol, I'm going to not even bother drawing that because you know that that also forms every single time we break it apart. The original backbone comes back to us. And all that we're saying now is if this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, that original carbonyl, instead of being protonated, is now a negatively charged ion. It has to have a first name to balance electrically. In the presence of the base sodium hydroxide, the sodium ion will now serve as that positive charge for that carboxylate ion. We would have CH2 taken 12 times, ending in a methyl group, giving me 1 plus 12 is 13, plus 1 more is the 14 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the same, so 2 of them so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 3 identical molecules of that soap. Down here in our next example, again, the glycerol backbone is released and we break the ester linkage. We break the ester linkage, and in doing so, I missed that bond right there. We break it here, the ester linkage, and we have to figure out what comes out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the same as above. We'd have our salt group, the negative ion of the carboxylate. That's a negative, it just strayed there. Let me try to erase that. There we go. And here's the carboxylate. We'd have 12 carbons ending with the terminal chain for a total of 14. That's what we ended here with. Here is carbon 1, 2, 3, 4, 5, 6, 7, 8. So in this group, we would have CH2 taken 1, 2, 3, 4, 5, 6, 7 times, and then I see a double bond, and then 1, 2, 3, 4, 5 more CH2s, ending with the methyl group to end the chain right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. These guys are identical, so I'll just show that there's 2 molecules of that particular soap that are formed as well. Let's end our lesson here, and when ready, come back for phospholipids, and then you'll move to your reading next.